Again, just like I did with the binomial distribution, I think we need to discuss what we mean by each of these 6 words. Okay? So I've got variable, I've got discrete variable, I've got constant rate, I've got unique, I've got independent, and then finally I've got Poisson. So can I just give you a couple of minutes, and I'm aware some of you may have it open on the slides in front of you. Can I just give you a couple of minutes to think what those words mean in the context of what we've just looked at, so with the heart rate? Okay? Let's discuss what we think we mean by these words. So in this case, what is the variable that we were just looking at? Yeah, the heartbeat, right? So in this case, it's the number of heartbeats that we have within some given time period. And again, when you define your random variable, you always have to define the time period, okay? Okay, why is this situation discrete? Yeah, you can't have like half a heartbeat. It either beats or it doesn't, yeah? So you can't have like 0.3 of a heartbeat or half a heartbeat. You can only have an integer number of heartbeats. Hence, it has to be discrete, okay? Absolutely. So you're dead right. You're dead right. When I got you to write down those 5 numbers and calculated the mean, you're totally right. It could come out as a non-integer number. But of course, you don't expect it to be a non-integer number because heart rates are meant to be integers, right? So in that case, you should probably take either the median or the mode, yeah? Because then it will definitely be an integer number. Does that make sense? So as long as it's discrete, it has to be, yeah. Exactly. I mean, you can take the mean if you wanted to, but you would have to round, yeah? Because you can't have a sort of 1.5 or something like that. Yeah. Good. What do you think we mean by constant rate? I think we've kind of discussed this one a little bit. Yeah, it kind of stays the same, right? So it happens, so the probability of getting 6 heartbeats with any given 10-second period will always be the same. So if I got you to stand up now, okay, exactly the same thing, count the number of heartbeats that you get within 10 seconds, it should be relatively the same. Does that make sense?
But it should be under the condition.
Yeah, exactly. So if we were like running around or something like that, then obviously the heart rate would change. But let's suppose we could redefine our random variable slightly, the number of resting heartbeats. Yeah, yeah. Because you're dead right, of course it will change slightly depending on the situation. But yeah, there should be conditions there. Good. So does that make sense what I mean by constant rate? If I got you to stand up again and do it for another 10-second periods, it should be relatively the same as what you got before. Yeah? And in fact, those 5 numbers that you got down, that you wrote down for me, they should be relatively the same. Am I right? Yeah? Good. Okay. So unique. Well, what I mean by unique here, it's a bit ambiguous, is that 2 or more events cannot occur at exactly the same time. Now just think about that with regards to the heartbeats. Why does that make sense? So 2 or more events. So what are we defining by an event here? The event is the number of heartbeats, right? So you can't get, in a 10-second period, you can't get 13 heartbeats and 14 heartbeats at exactly the same time. Yeah? So within the same time period, you can't get both 13 heartbeats and 14 heartbeats. You either get 13 heartbeats or you get 14 heartbeats, but they can't occur together. Does that make sense? Yeah? So they can't occur at exactly the same time. Independent then, what do we mean by independent? Well, each set of heartbeats is not influenced by another. Does that make sense? So each of those 10-second periods that I got you to count through, they weren't influenced by the previous 10-second periods. Is that okay? Good. And then it's Poisson because something happens at a constant rate. The random variable that we're dealing with here happens at a constant rate. Okay? So just think, you've now got 3 distributions hopefully in your head. You've got the uniform distribution, which is where each event has an equal outcome. So each event has an equal probability of happening. Okay? You've got the binomial distribution, success or failure. You've now got the Poisson distribution. The Poisson distribution is characterized when you have a random variable that happens at a constant rate. Is that okay? Those 3 things cemented in your head? Happy with that? Good, fantastic. So we've already kind of discussed this, okay? We have our now Poisson distribution, which we write like this, okay? I've used a slightly different example on the board. Like I said that my rate was 7. Up here I said that my rate was 13, okay? So in general, the rate at which something happens is the only parameter that we need for a Poisson distribution. Is that okay? Yeah, are there any questions about that? So, can you can you think for me of any other situations, any other random variables which would be distributed using a Poisson distribution? Can you think of any other examples in real life? So I'll tell you what, I'll give you 3 minutes to discuss on your tables. Okay, so what do we reckon then? What are your suggestions? What do we reckon? Sorry? A clock, absolutely. So the number of times that hand moves within a given time period. Perfect. Any other suggestions?
Rotation of the Earth around the sun.
Rotation of the Earth around the sun, that's pretty constant to me. Yeah, absolutely. Any others? Movement of tectonic plates. Oh, that's an interesting one. Why do you say that?
Because it's relatively average and constant for each single plate.
I would agree with that. Yeah, no, I would agree with that. Yeah, that's an interesting one. Quite an unusual one, but yeah, go on. That's fine. Any other suggestions, boys? Yeah, waiting.
The alternating current.
The alternating currents. Ah, interesting. Yeah, absolutely. Yeah, so you're talking about electricity?
The phase shift.
Absolutely. Do you know what it is in this country? So within 1 second, do you know how many phases there are? How many alternatings there are? It's 50. Yeah. So 50 in a given second. Yep. Any other suggestions? Yeah, absolutely. All those kind of things. Yeah. Even things like Twitter. Okay. The number of tweets per minute. Right. That remains relatively constant. YouTube, the number of videos uploaded every second, that remains constant, yeah, because it's happening so often.
This company closed.
If it closed, then that's a different story, but yeah. Sorry?
Is it at the same rate?
Yes, it's pretty much the same rate, yeah. Because there's so many people using the website that actually, because it's global, it remains relatively constant. It's true, just check it out, yeah.
Because the sample is big, maybe.
It's a big sample. Yeah, that's the key. Obviously, if it was just in this country, so for example, the number of people watching television would not be distributed using a Poisson distribution because not everybody would be awake at certain times. So obviously, during the day, there'll be like a peak time where there's lots of people watching television, but then at night, obviously, there's a much lower rate, if you like. There's a much lower chance of people watching television. Yeah.
The same theory applied to Twitter, right?
Not true, because it's a global entity. People around the world are using it. So even though people in this country might be sleeping and not necessarily using Twitter, people in another part of the world, the other side of the world, who will be during the day.
Same as television. This part of people.
Okay. So you need to be careful how you define it, right? If you're talking about global television watchers, absolutely, I agree with you. If you're just talking about television in this country, then yeah, it wouldn't be. Yeah. So it's all to do with how you define that random variable. So if people don't write what they mean by the random variable, if you don't define it, like it's open to interpretation. It's the importance of defining your random variable. Yeah? Good. Excellent. Right, okay. So just for the sake of clarity, okay, I've changed the random variable slightly. Okay, well actually I've changed the parameter of the random variable. So we've still got the number of heartbeats in a 10-second period. Okay, but now instead of it being 13, which is the number we came up with before, I've just changed it to be 7. And that's then makes sure it's consistent with what's on the slide. So obviously when I put these slides together, I didn't know what the outcome was going to be. Okay, so I've just chosen it to be 7, right? Now, you notice that I've drawn the probability distribution on the board. So I've got the outcome, and I've just selected some outcomes. I've got 4, 5, 6, 7, 8, 9, and 10. These are the different outcomes that you can get in a given 10-second period. Okay? So if somebody else were to stand up now, count the number of heartbeats in a 10-second period, it could be 4 heartbeats, 5 heartbeats, 6 heartbeats, 8 heartbeats, 9 heartbeats, 10 heartbeats, 7, 11, 3, 2, 1. It could be different ones. Okay? And all I've done is I've written the probability that is associated with each of these outcomes. Now, how do you calculate that probability? It is in the slides, okay? And it is something that you may want to familiarize yourself with. However, it's a bit gnarly, so we're not going to go through it. All I'm going to tell you is there is a way of calculating it, and I will give you the formula in the formula sheet. So if I do need you to calculate it, you can use the formula in the formula sheet. Okay? If you're interested in where it comes from, like I say, it is in the slides, and you are more than welcome to look through it. Okay? So, what do you think, given that x is distributed using a Poisson distribution, with a rate of 7 heartbeats in a 10-second period, what do you think, in this case, the most likely outcome is going to be? 7, absolutely. And you can see that quite easily from the probability. It's the one with the highest probability, okay? And can you see that as you move away from 7, so if you move to the left, 6 heartbeats, 5 heartbeats, 4 heartbeats, etc., it becomes increasingly less likely, yeah? And again, if you move in the other direction, so 8 heartbeats, 9 heartbeats, 10 heartbeats, again, it becomes increasingly less likely. So are you surprised that if we were to graph the probability mass function of this, you get a shape like this? Are you surprised by that? No, not particularly. Like, you expect the number of heartbeats to be 7. That's the one with the highest bar. And then as you move away from that, the probability becomes less and less likely. Does that make sense? Do you recognize that shape? Where did we see this before? Binomial. We saw it yesterday. Okay? So remember, right at the beginning of the lesson, I said a Poisson distribution and a binomial distribution are related in some way. And this is the first link that you're starting to see. So this probability mass function is pretty much identical to the probability mass function for a binomial distribution. Does that make sense? Okay. So can I give you 2 minutes then? If you've got the slides open in front of you, can you click on this link? Can you click on this link? If you haven't got the slides open in front of you, I've linked it on the VLE. Can you open this link? And can you just see what happens if you change the parameter for the rate? So if you change 7 to 8 or 9 or 10, and can you just tell me what happens with the probability mass function?